Hey teachers, do you sometimes feel like a section is never going to end? I feel like that right now. There's a lot in this one section, 2.2, a lot about sets, but we're almost finished. Just hang with me. It says given A is equal to 1, 2, 3, 4, 5, B is equal to 1, 3. Hey, we just did this. Oh, hey, watch the end of the last video. We did the proper subset thing, remember? Just a real quick recap. Proper subsets. Remember what a proper subset is versus a regular subset? Let's talk about it. Let's look at B. Set B, 1, 3. Oh, set B, 1, 3 right here. And set A, 1, 2, 3, 4, 5. Notice how all the elements in B are included in A. That means B is a subset of A. But because there are elements that are in A that are not in B, for instance, 2, 4, and 5, that also means B is a proper subset of A. The notation is great because this equal extra line that makes it almost look like an equal to is letting you know that it's okay for B to have exactly the same elements as A. Because we could say that B is a subset of B. But you can't say B is a proper subset of B, because there has to be elements in B that are not in B when you talk about proper subsets. So that you can't say. All right, so we talked about that at the end of the last video. I think you're comfy with me on that particular situation. Let's do a different problem. Inequalities and applications of set concepts. So what we're going to talk about here, suppose A and B are finite sets. What does that mean? They don't go on and on forever. They're not infinite. So their cardinality, which remember is how many elements are in the set, is either 0 or a natural number. So if A equals B, then the number in A is equal to the number in B, or the cardinality of A is equal to the cardinality of B. And A and B are equivalent, because if the sets are equal, they are also equivalent. It's possible to establish a one-to-one correspondence between A and B. Remember, that's what equivalent, that's actually the definition of equivalent, is that you can establish a one-to-one correspondence, and all equal sets are equivalent. But then it goes on to say if A is a proper subset of B, right? That means there's elements in B that are not in A. So the number in A, or the cardinality of A, has to be less than the cardinality of B. It has to. And it's not possible to establish a one-to-one correspondence between A and B. Again, quick example, right? So if I give you the set 1, 2, 3, let's call that A, and B is the set 1, 2. Okay, they are not equal sets. All right? I can say that B is a proper subset of A. Why can I say that? Because 1 is included in set A, and the element 2, which is in set B, is also included in the set A. Moreover, A has an element 3 that's not in B. That's what makes B a proper subset of A. Well, what about the cardinality? The cardinality of B, or the number in B, is 3, right? 2. Woo. No, copy that. Okay. Try again. The number in B is 2. All right. What's the number in A, or the cardinality of A? That's 3. So you can say 2 is less than 3, of course, and you can always say if B is a subset of A, proper subset, then the cardinality is also less. But this gets weird when you start talking about infinite sets. Okay, so N, you know what N is, right? It's the natural numbers. Starts with 1, they're counting numbers. And W is saying the whole numbers. What's the difference between the natural numbers and the whole numbers? 0. Just the one number 0. But they're saying that we could find a one-to-one correspondence between these two. Even though it doesn't make sense, they don't have the same number of elements, do they? Because 0. 0 is an extra guy. If you take the natural numbers and you combine that with 0, then you get the whole numbers. Okay, but notice they say it's still possible to establish a one-to-one correspondence between the sets by letting each element in N correspond to a number in W that is one smaller. So N, the natural numbers, is equivalent to the whole numbers. Is that not weird? It still bothers me. It bothers me. But because they're infinite sets, you can still set up a one-to-one correspondence. And then that's got to be okay. And it's measuring infinity. And they have the same level of infinity. They have the same cardinality. Very, very interesting. Still a little disturbing, but it's interesting. Almost done. If P is equal to the set A, the only thing in the set P is A. I'm sorry, the element A. Then P has two subsets, right? Because you have the set and then the empty set. And what is a subset? Is every single possibility of elements that are in that set. The empty set, by the way, let's put this somewhere. The empty set is a subset of every set. What else is a subset of every set? The set itself. So P is also a subset of P. Always. Those two guys are always subsets. So there are two subsets if you have just a one element set. What if you have a two element set? That's this number 2. If you have A, B, then Q, the set Q here has 4 subsets. How come? Because remember, the empty set is a subset. The set itself is a subset. And hey, you could do A by itself and B by itself. Notice I'm just rewriting what they have written here, but I want you to see it kind of in real time. So again, if you have one element, you have 2 subsets. If you have 2 elements, you have 4 subsets. Look at this list. I'm not going to redo this for us. If R is the set ABC, it has 3 elements, right? Then you have the empty set, which is a subset of every set, and you have the original set, which is the subset of every set. Then you could also do each of the elements alone. There's the set with just A in it, the set with just B, the set with just C. Then what could you do? Combine together every possible way you could, 2 elements at a time. You could put A with B and A with C. Then you could put B with C. Can you switch them up? What about C with B? Well, we did that already. Remember, the order of sets doesn't matter. How many is that? That's 8. Is there a pattern? You bet there is. So if you have n elements, the rule is the number of subsets is 2 to the n power. So back to number 1. Let's do this in red so it's easy to spot. Okay, so it's 2 to the first, which is 2. That's that 2 that we counted over here. If you have 2 elements, that's 2 squared, which is 4. That's the 4 we counted here. If you have 3 elements, 2 to the third, which is 2 times 2 times 2 is 8, right? Not 6. Y'all be careful. 8. And that's the 8 we counted here. One more, and then I'm done, thank goodness, with this long section. How many subsets can be formed from the set A, B, C, D, E, F, G? Now, do you want to write them all out? I don't. It's going to take a long time, right? You've got the empty set. Look, if we started writing these things, think about it. You've got the empty set, and you've got the whole set itself. A, B, C, D, E, F, G. Then you might want to see, then you've got A, and B, and C, and D, all the way down. Then you've got 2 at a time. A, B, A, C, A, D, A, E, A, F, A, G. Then B, C, B, D, E, B, E, B, F, B, G, all the way down 2 at a time. Then you do 3, A, B, C, A, B, D, A, B, E, A, B, F, A, B, G, right? You don't want to do that. And they didn't ask us to list all the subsets. That's a different question. They just wanted to know how many. How about 2 to the what power, y'all? Well, it's got 1, 2, 3, 4, 5, 6, 7 elements. So it's 2 to the 7th power. 2 to the 7th power. I don't have memorized at the moment. So 2 to the 7th is equal to 128 subsets. Do you want to list all those? Nope. Nope, you don't. All right, y'all. Let me know how it goes. Have a wonderful day. This wraps up section 2.2.